if you think about RNNs in general, they are a very general trainable model that maps variable length sequences to fixed length vectors. In fact, thanks to the sequence generation and beam search that we've just discussed, they can also be made to map fixed length vectors to sequences. Start from a vector, map it to the state of your RNN, then produce a prediction. Then sample from it or use beam search and feed them back into the RNN to get the next one. Now you have those two building blocks and you can stitch them together. It gives you a new model that maps sequences of arbitrary length to other sequences of arbitrary length. And it's fully trainable. What can you do with this? Many things. Imagine that your input is a sequence of English words and your output a sequence of French words. You've just built a machine translation system. All you need is some parallel text. Imagine that your input is sounds and your output words. You've just built an end-to-end speech recognition system. Real systems based on variations on this design exist and are very competitive. In practice, they do require a lot of data and a lot of compute to work very well. We've also talked about convnets, which basically map images into vectors that represent the content of that image. So picture what would happen if you took a convnet and connected it to an RNN. You have an image going in and a sequence of things coming out, a sequence of words maybe the caption for that image. To do that, you need training images and captions. There are a few data sets out there that you can use for that, most notably the COCO dataset. It has images and crowdsourced captions for them. You can train a model that uses a convnet to analyze the image and generate captions from them. And it works. You can get great captions, generated completely automatically, and it sometimes fails in very, very funny ways.